topic for today. So I'm going to finish the air resist the friction force. But this friction force is not going to be about the solid contact. We're going to talk about what happens if the media is the fluid, such as like water or air. And you also have a resistance. That resistance is what we call the drag force. It just tries to slow you down. The second part of this topic is about the uniform circular motion. This one is kind of important. So we're going to talk about what happens if you have a circular motion and what will be the result and what will be the equation that you can use. It turns out when you have this kind of motion, you're going to have an acceleration. And that acceleration is based on some property, and we're going to show you the equation. And that will be an equation that you should know, and you probably will see at least like one question is going to ask you about these. So the circular motion is also an important motion. So the idea of this here, let me change that to my pad so I can write something on top of my pad, then you can see my notes. Let me join. Okay, I'm not going to put a lot of emphasis on the drag force. It's just one of the idea I wanted you to know. So when you watch the video, then you see. Okay, can you guys still hear me? Anyone?
Yep.
Yes.
Thank you very much. And I'm sharing my screen. So you guys can see my screen, right? All right. Let me show you the example first, and then I will go back to the main topics of the topics. So over here, after I finish the lecture, I will briefly talk about these three examples. And these are the example I pre-recorded, and then you can watch the video to understand how we deal with these three different situations. Okay, so these are three different examples to give you an idea how to apply the topic of today. Now, just to that you understand well how we actually solve the problem, and I'm going to start with the drag force. As I said, the drag force simply represents like a resistance force, very similar to the friction. And for the friction, we have certain rule. Friction always has a direction which is against the direction of the motion. So if you move into the right, your friction go to the left, try to stop you. If you go to the left, then the friction goes to the right. So that's how the friction force is. So when you do the friction, that you always deal with the magnitude, and then you think about the direction is opposite to the direction of the motion. So that's how we deal with the friction case. Over here, the drag force is the same. If you have an object moving to the right, then drag force will be going to the left. The equation that we write over here. There's two kinds of a drag force. If you're looking at the object, which is a very small, like a smaller than like a ping pong ball maybe, and you're moving with a slow speed. Well, we didn't really give you, like how small that should be, but usually if you look at a scale like a molecule or like a cell, a book talk about a lot of example relate to the biology, and for those kind of a scale of the mass, then and you think about how fast they can move, they won't move very fast. And then we can just simply use the B times V model. And if this is larger, such as a human being, or you have a car, you have an airplane, and they are large, but they move very fast. Well, human being not going to move very fast. But if you are dropping from a height like you jump out a cliff, then your speed will getting faster and faster, then you will be modeled as the larger object with a faster speed. So that would be c times v squared. The important thing I want to point out is this v over here. This v represents the speed. We don't use the velocity, and the reason we didn't use the velocity was because it only depends on the magnitude. As you can see, it's a magnitude square, so it make no sense that you include the direction. The direction we know is always opposite to the direction of the motion, so we don't include the direction. We only care about how much is that. It's a v squared, so it's not simply just proportional to the speed, so it has a larger effect by the speed. Now, what about the b and c? Well, the b and c are the constant. B and C are the constant which include anything else but the speed. The shape of the object and maybe the material of the object will actually affect how much of the drag force is, such as the roughness of the surface might also have some impact to this drag force as well. So if you have a very smooth bowl opposed to a very rough surface bowl, and they are moving at the same time with the same velocity, but they are not going to feel the same kind of drag force. So all these other kind of situations, we put it into a constant. Normally the constant will be given to you, and there's no way that you can figure out the equation for the constant. So that's why we just use a constant. So that's about this, the last part of this. And when we see the example, you will see how we can apply that. You just treat that as a force. Treat it like a friction force. Any question about this part? Okay, let's look at the second part. The second part, the uniform circular motion, is when you have an object and is moving along a circle. And particularly when you're moving along a circle, it doesn't change its speed. Okay, I didn't say velocity, it's speed. The speed meaning the magnitude doesn't change. So if you have a circle like this, I have an object here, and let's say it's moving clockwise. I use the length to represent the speed, so this is the speed, and the speed is going to the right, but with some amount. When you move to the right-hand side, you are going to have the same length to represent the speed, while the speed is still the same. However, how this arrow points to represent the direction. So direction is different. If I give you this problem and I ask you, are they have the same velocity? Then your answer should be what? There should be no. And the reason is no was because they don't have the same direction. They have the same speed, but not the direction. Therefore, the velocity is not the same. So same speed but different velocity because of direction. When you have a different direction, you can create an acceleration. When you have different speed, you can also create an acceleration. So you can create acceleration in two different ways. Actually, you can also have a combination by changing the speed and also change the direction. So this is one of the cases that you only change the direction, but you don't change the speed. And that's the special case they were dealing with at here. When you have this situation, that means you have the change of the velocity. And how do we define acceleration? Acceleration is the change of velocity. It's not a change of the speed, only it's the change of velocity. Remember that? So it's change of velocity of change of time. So if you have the change of direction, you will create an acceleration. If you have the change of the speed, you will have acceleration as well. If you change both, you're certainly going to have an acceleration. Okay, so that's an important concept about this kind of motion. Now, how do you visualize this? Why did you have an acceleration, and where is the acceleration going to? And that's the topic for today. How do we find the change? When we define the change, we say this is the velocity of the final minus the velocity of the initial or the earlier, the later minus the earlier, or the final minus the initial. That's how we define the change of the velocity, right? And the change of the time. In the vector, if you have this kind of thing that you wanted to do the operation, or you wanted to find the difference of that, how do you do that? Well, you have two vectors. One is the final velocity, one is the initial velocity. Let's just say this is your initial, and this is your final. And I want to find a change. I will start with my final. This is my final. And minus the initial. And how do you use the arrow to represent a minus initial? The minus initial simply just opposite to the initial. So my initial was going to the right. Then this time I'm going to write to the left. So that will be my initial velocity. Our net change is from the starting point to the end point of the second vector. That will be the VF minus VI. That is the change of the velocity. Okay. If you make these two closer and closer, and you're going to see the change of velocity, if it toward to the direction of the center, then your acceleration is going to have the same kind of direction with the change of the velocity direction, because time doesn't have a direction. So the only way that you can think about the direction of the acceleration is going to be the direction of the change of the velocity. And we just show you the red one, the delta V is the so you're going to have an acceleration. That acceleration is going to be the acceleration toward to the center. Okay, so that is an important conclusion that we can see from here. This acceleration, we give a special name called the centripetal acceleration. Centripetal has the meaning called centuries. The century is meaning the center. The petrol meaning seeking. So it's the center seeking acceleration. So this acceleration always toward to the center of the circle. Remember this? And let's write down the equation. You're not responsible to derive the equation. So I'm just going to give you the equation, and you have the formula sheet, and I put this equation already in there. The acceleration, the magnitude is equal to this. It's the V squared over R, where the V is the speed.
Okay, this is the speed in meter per second square and divide by the r, where the r is the radius of the circle. So this is in the r. And what is the unit of acceleration? By the way, I was grading your lab. A lot of people forgot to write down the unit. So remember, in the exam, you have to write a unit. Otherwise, you're going to have some points off if you didn't write a unit. So remember to write a unit. So this one, acceleration is meter per second squared. And if you just simply put a number with the unit inside of this calculation, you will find out, yes, the acceleration is going to be v squared over r. It's going to give you meter per second squared. So that's the acceleration. What is the direction? Direction is toward to the center. Okay, so this one here is the most important thing you have to know, and that's the equation that you're going to use to do the calculation. You have to know what is the centripetal acceleration, how do you calculate that, and what is the direction of that. Okay, question about this part. And let's explain what this is. If you have an acceleration, there must be something cause you have an acceleration. The Newton's second law is actually to give you this, the reason why you have acceleration. And what Newton's law give you that? Which Newton law give you an acceleration? Is it first law, second law, or third law?
Second law.
Great. Second law, the second law tells you the force, if you have a force is not equal to 0, you're going to have an acceleration. And if you have a centripetal force acceleration, that means you have a centripetal force. So you have an acceleration, that acceleration toward to the center, meaning you have a force. That force is the center-seeking force. That force is called centripetal force. That force is equal to mass times acceleration. So this one is equal to mass times this acceleration. And what is the acceleration? The acceleration is v squared over r. Toward to the center. Okay. All right, let me give you one example that I will talk about the example, then you can watch the video that I recorded. One simple example you can actually do by yourself is you can find a string. So get a string. And at the end of the string, just tie it to an object. Could be a ball or could be anything else. So you put your hand over here and you kind of swim it. When you swim it, because you have a string and it will go a circle, right? It will go around a circle. And if you cut off the string, what happened to the ball? If you cut off, this ball is going to fly away, and what direction will it fly away? Well, it depends on which position that is. If you swing the ball, the speed of the ball at this moment is going to go this direction. The direction is what we call the tangential direction. What is tangential? The tangential is the direction is perpendicular to the object to the center. So, for example, if I look at this one here, well, this is the direction from this object to the center. That the tangential is perpendicular to this one here, which is that direction. If you are moving at this position and your R is in this direction. So you make an arrow which is perpendicular to that dashed line. That is your tangential direction. And that's the direction of the speed of the bow at that point. So if I cut off the wire, the string, the bow is not going to go circular. It's going to fly away, right? And what kind of force is the string is going to give to the bow? What do we call that force?
I want to say tension.
Yes, it's a tension force. The rope gives you a tension force. Can you tell me what direction tension force is? Anyone?
The direction of the pull, right?
Direction of the pull, meaning it's going toward to the hand, right? This is your tension force. Without this tension force, the bow is not going to go circular. It's going to fly away. And what does that tell you about the tension force and the force we just introduced to you? What is the centripetal force? The centripetal force is the force toward to the center, right? So we force the ball to go circle was because you give a tension force. Now tension force is your centripetal force. Without that force, it's not going to have the center seeking property, is going to fly away. And that's why we call this the centripetal force. Okay, so it's also important as you look at my video of the example, important to make a free body diagram. So in this case, if I draw a free body diagram for this bow, and let me just draw that real quick. This is the bow itself, and it's going like a circle. It's horizontally, so I don't need to care. I don't need to worry about the gravity. Okay, it's horizontal, doing a circle. And what kind of force acting on this bow in this case? It's the tension force. And what is the result of this? Result of this is that this is going to go along a circle and it's going to create an acceleration, right? And that acceleration is a sub cent. What is the direction of this acceleration?
Inwards.
Inwards, great. So that is this direction, that is the cent. Now, when you have an acceleration, meaning you're going to have force, and that force is the centripetal force, and that is the net force. So your net force is the T, and that is your centripetal force. And that centripetal force is equal to mass times the A of the cent, and that A of cent is the V squared over R. Okay. Now, if you didn't, so let's say you have the string you tie with a bow and you swim it. If you swim it too slow, what happens? If you swim it too slow, this V is going to be slow, it's going to be smaller, and you are not going to give a larger, like a tension. It's not going to get the circle. It's not going to go around a circle. And if you give a larger force enough, then you can make it go around a circle. Another thing you can think of this is that if you swim the bow how long the string, how long the wire is going to affect how much speed that you need in order to keep it going around a circle, right? If you have a longer distance of the wire, do you think you need to swim it faster or slower?
Faster?
You have to swim it faster?
Yes.
And how do you actually figure out in that way? So if I write the big R represent a longer, if I write smaller R represent a smaller, you have a V, and this is a V square. So if you increase the R, and if the tension is the same, then your centripetal force is the same, you need a larger speed. But remember, this is not simply just V, this is a V square. So that's the key thing that you have to understand. All right, any question about this part? The most important thing, again, is the blue color that you see on the screen, the centripetal acceleration equal to V over V square over R, and the direction is toward to the center. Let me briefly talk about the three examples that you can go back and watch the video to figure out the whole thing. The first idea that we are introducing over the first example is so-called the terminal velocity. The terminal velocity is a situation when you have two forces or acting on an object, the object is moving, and when the forces are the same and at the opposite direction, you will make the object experience no net force, but you are moving. That situation is like you are on a parachute. So when you jump out from an airplane, you are attracted by the earth, you're going downwards, so the only force acting on you is the gravity. At the same time, if you open the parachute is going to get the area larger such that you can have an air resistance. The air resistance is going to be on the opposite direction of the motion, so it go upwards, but you are falling down, so you go downwards. If these two forces are the same, you're going to have a situation called the terminal velocity. And it only happened at a certain period. So at that case, you're going to have a situation, the force of the drag force equal to the force of the wave, where you can see on the right-hand side over here. So when you have these two forces are equal, then you're going to have a velocity called terminal velocity. And you can use this example to figure out how this drag force is. The second example that we give you is a situation that you have a circular motion. This circular motion is like a Ferris wheel. So if you go to an amusement park and they have this Ferris wheel, and if you still remember when you are taking this wheel and when they circulating around like a circle, let's say they circulating in the same speed, do they have the same velocity? No, circular motion has the same speed, but a different direction, so you don't have the same velocity, okay? Then this is a circular motion. The circular motion, this question tells you when you are actually on the Ferris wheel, why do you feel differently when you are at a different position of the wheel? And we compare two of them. The one is at the top and one at the bottom. What you feel when you sit on this kind of Ferris wheel is the feeling from the chair. So what you feel is actually a reaction force, just like you try to measure your weight. The weight is a reaction force. It's the force coming from the scale. So it's a normal force. It's a supporting force is the weight. Same thing over here. What you feel from your butt is the chair pushing on you. And your feeling is going to be different. By looking at this example, we will tell you why you feel differently. You can also do a calculation to find the difference. Okay, any questions so far? The last one here is very similar to the example I just talked to you with a string holding with a rope, with a ball. Now, you're sitting on a merry-go-round. Merry-go-round is the horizontal plane, and this kid sit on there. If this wheel, this merry-go-round start to turn, what happened to the kid? What happened if this speed is very fast? You're going to fly away. All right, this kid is going to fly away. And if the speed is not larger enough and this kid is not fly away, and then what is the reason he doesn't fly away? There must be a force to prevent it fly away, just like the rope. But here we don't have a rope. Instead of a rope, what kind of a possibility that you can think of that will give you a force that is not going to fly away?
Friction.
Yes, the friction. So the friction is the force to prevent it fly away. How do we find the friction force and is related to the friction coefficient? There is a static friction force, and the static friction force has a maximum static friction force that is equal to the mu s times this one here. What does the n represent?
Normal force?
This is a normal force. How do we calculate normal force in this case?
Mass times gravity?
Correct. It's how much force coming from the weight against the surface of the contact, which is the weight, which is the mass times the gravity. And this is 90 kilogram. So 19 multiplied with 9.8 is your n. How do you find out how much friction force is needed? Well, in this case, friction force is your centripetal force. And that is equal to m times a cent. And that is equal to m times v squared over r. That's how you figure it out. Okay, there's another thing that's about the speed. I think you can watch the video, and that is another important part of figure out how to get the speed in this case.